We're doing a review of vector, and I want to put this into some context. The context that we're working on here is one of the things we want to do in Engineering 1301 is get you some practice and expertise in applying engineering models to the real world. Okay, and the way we're going to do that is we're going to take a look at some little tiny baby problems, basically, in statics. Statics is the study of the forces that are involved with things that are not in motion. If it's a car and the car is in motion, then it becomes more of something that we'd call dynamics. So we'll get into statics, and then we're also going to take a look later in the course about the topic of circuits. All right, and we're going to see there's some analogies between the two. I think that's a cool thing. But along the way, we're going to talk about applying principles and models to solve for forces in a static system or voltages and currents in circuits. Okay, so it's a process. What we care most about is the process, and so we're not going to get to real complicated problems, but we're going to get a step-by-step approach to being able to solve some real-world engineering problems. All right, so that's the steps. Along the way, we're going to need various topics, and in this case, we're going to need vectors. Now, I'm assuming this is somewhat of a review for you. If you're rusty on that, that's okay. I remember when I first started college, it was like, oh yeah, I had vectors, but when I saw it again in the context of actually solving problems, it became much more interesting to me. It's like, this is why this is useful. Okay, so let's take a look. With a vector, we're just going to basically work on examples. All right, so we're going to talk about this in terms of examples. Okay, so in the first example, let's take a look at a vector. All right, so I'm just going to make one up. I'm going to call it A, it's a vector A, is equal to 8I plus 4J. Okay, so we're letting I be a unit vector in the x direction. Okay, so if I drew a picture of I and, I draw that in red, here is the vector I. Okay, so we just can scale that and get up to 8 times I. All right, so let me get rid of that and make this, I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, and then I'm going to go up J. J is a vector in the y direction, so there's the J vector. All right, so count up 4, 1, 2, 3, 4, and we have the vector A. All right, so I'm assuming you've seen something like this before. You might not have called it I and J, but you get the point. You take 8, multiply by I is that unit vector in the x direction. You take J, which is the movement in the y direction, multiply that by 4, and you get this vector A. Okay? Well, a lot of times it becomes important to look at representing A in terms of its length and its angle. Okay, so this would be a polar coordinate if you had polar coordinates in high school. All right, so we could take a look at the magnitude of A. Okay, so the magnitude of A would be this length, and we know from the Pythagorean theorem that this would be 8 squared plus 4 squared, square root, Pythagorean theorem. Okay, all right, so I didn't calculate that number, but you can get A. All right, theta is a little more complicated. All right, so I think that from trig we would have tangent of theta would be the y component, AY, divided by the x component. Okay, and so if I wanted theta, it would be the arctangent. Okay, and so I'm going to go over the side here. You could do this in your calculator. You can also do it in Matlab. Okay, the thing about Matlab doesn't really have a degree mode or radian mode, it's always going to give you radians unless you use a specific function name that pulls back things in degrees. Okay, so we're going to do the degree function. So we're going to do arctangent, so that's not a surprising name, but we're going to add this d at the end. The d means the answer shows up in degrees. Okay, so the y component was 4, the x component was 8. We do that calculation, we get 26.57 degrees. And you know, that looks about right. All right. So there we go. That's example number 1. All right, let's do another example. Let's take this coordinate system. And this time let's do -8. All right, I'll use purple. 1, 2, 3, 4, 5, 6, 7, 8. Plus 4. 1, 2, 3, 4. So this is going to be my vector B. Okay. So I could write that as B is -8I plus 4J. All right, I think that makes sense. All right, and if I wanted to look at the magnitude of B, really the only thing that happened was that the x component was in a different direction. It was negative instead of positive. So it's still -8 squared plus 4 squared square root. The length of B did not change. Okay, but if I wanted to find the theta, the angle theta, what would you do? Okay, so I think a lot of us would do, well, theta is going to be the arctan, and I can use that in degrees, of the length, the vertical height. Okay, so that'd be 4 divided by 8. Okay, and so I would get the same answer, 26.57. That would be this angle. All right. But normally, when we reference a vector, we reference it to the 0 degree axis. Okay, so let me draw that in red. Okay, so normally we would want theta to be here. Okay, and so I think you've probably had enough trig to know that theta in this case would be 180 minus, I put that theta, I should call this, let's call this alpha so that we're consistent. Here's alpha. It'd be 180 minus alpha, and when we go through the calculation there, that would be 153.43 degrees. Okay, so we could reference, you know, the angle or the vector B. You know, the shorthand notation I use for that is B is equal to the magnitude of B at angle 153.43 degrees. Okay, where the magnitude of B is whatever comes out of this number. Okay. All right, so the reason I mention that is because I want to point out tricks as we go along on the road here. It was a little tricky to use your calculator to find the reference angle, okay? And so you may have become aware in high school of a tan2 function, okay, or an arctan2 function that lets you keep track of quadrants without having to, you know, think about it too hard. What we did here was we drew the picture, and then from the picture we could tell that theta was going to be 180 minus alpha. What if we had a way of doing that where we don't have to do that mental calculation? Okay, so it turns out you can do that. It's in Matlab is a tan2. All right, you have that on your calculator if you have a good enough calculator. Okay, so like if you had a TI-89 calculator, there's an arctan2 function in there. Okay, It takes 2 arguments, all right, because it's going to try to keep track of the quadrants. And the quadrants, it matters, which one's y and which one's x, all right. So it turns out we can calculate theta directly by a tan 2. We use the vertical first, okay. In this case, the vertical was 4. We use the horizontal second. The horizontal was -8. And coming out of that is our answer, where we didn't have to, draw the picture and do the quadrant conversion. Okay, so I wanted you to be aware of that so that you could maybe start practicing using A10 to, anytime we can reduce sort of the brain power load, where we don't have to think about things as hard, and still get the right answers, I think that's a good practice to take. Okay? All right. The next thing I wanted to do is talk about adding vectors. I'm assuming, again, this would be a review, but it's useful to do it, and if you're rusty at it, you can practice it. We're going to give you some practice problems. Okay, so let's say A is equal to 3i minus 2j. And let's make a vector B be 6i plus 2j. So this is yet another example. All right. We can find a resultant vector C, which is the addition of A and B. Okay, so what I want to do at this point is draw it. All right, so I think we know that what you do is you add up the components. All right, so you add up the components in the I direction, and you add up components in the j direction. So I is going to be 3 plus 6, which would be 9i, and then the j components, minus 2 plus 2, gives me 0j. Okay, so the resultant vector is 9i. Okay, so I'm going to draw that. All right, so let me change the pen color, put down an axis. Okay, so A is 3i. Okay, so I go over 1, 2, 3, minus 2j. Here is the vector A. Okay, I'll change my pen color. Okay, the vector B is 6, 1, 2, 3, 4, 5, 6i plus 2j. Okay, so that's, oops, I passed it. Sorry. So that's the vector B. Okay, and so what you know, hopefully, is that vectors add tip to tail. All right, so I can pick up this vector B and put it from the tip of A, I'm sorry, the tail of A, I put the tip of B. Okay, and you see it adds up to C. If you count these units, it lands back at 0 at 9i. Okay, so I did it that way, and I could redo this. Put this back, I think. I've got it messed up. Okay, put that back, grab the vector A. All right, so here's supposed to be A. Put it tail to tip, and it lands, of course, at C. All right, so finishing off the drawing, we have the vector C showing up here, and it's just tail to tip. All right, so you've probably seen that before, but if not, there's a preview of how that works. All right, so the next thing that we do, and it's going to be important, is we need to be able to come up with resultant forces. All right, so many times we'll have some set of forces operating on a point. Okay, so I have this example worked out where I have a force The magnitude of this force is going to be 10, and the angle that it operates between, well, as shown here, is 20 degrees. Okay, I'm going to add another force. I'm going to make that a bigger force. It's going to be a magnitude of 15. This angle between horizontal, but it's pointing back the negative direction, so that's okay. We can figure out the trig on that. Okay, 15. That angle is 40 degrees as shown in the diagram, and then I'm going to have a third vector pointing down, and that vector is also going to have a length of 10. Okay, so we can put some labels on here. Let's call this one A, this one B, and this one C. All right, so if we had all these forces operating on that point, it can be represented with an equivalent force. Okay, so the resultant equivalent force is just the sum of the vectors. All right, so A plus B plus C. All right, but to get that, what we do is we add the vectors in the component directions. Okay, so we figure out what Rx is, and we figure out what Ry is. Okay, so basically you can decompose these into the I's and the J's. All right, and so I look at this. Let's consider first Rx. All right, so I'll get rid of this. Okay, so Rx is going to be Ax plus Bx plus Cx. Okay, now I look at this. A is pointed in the positive direction. Okay, so if we say this is positive, to the right is positive, just like the number line. Okay, then Ax is going to be 10, and I do my trig work here. You know, cosine is, you know what cosine is? It's adjacent over the hypotenuse. All right, so cosine of theta, to get the x component, you would do 10 times the cosine of 20 degrees. All right, so hopefully that's obvious. All right, next. All right, so you see that? You take cosine of 20 degrees and you get this value. It's back to trig. Okay, then for Bx, we see there's no x component, so that would be 0. All right, so let me highlight these things. Ax is this, all right, Bx is 0. Okay, and then finally, Cx works back to the left, so that would be subtracted, so that's minus 15 times the cosine of 40 degrees. Okay, so I put my calculator in the right mode, or I use Matlab with the cosine d or the the cosine d functions so that I get the right answers. If you use your calculator in radian mode, you'd have to calculate this 20 degrees, convert that back to radians. Although in your calculator, if you actually put in the degree symbol, that tells the calculator, oh, I want this converted into radians. Okay, so work on using your calculator or Matlab to make sure you can do this. Okay, so Rx, in this case, when we add all these numbers together, you get minus 2.09 as the answer. All right, next, what would we do for Ry? Ry would be the same idea. We're resolving things in the y direction, ay plus by plus cy. Okay, and so taking a look at the diagram, A is moving upward. All right, so we resolve that using trig. That would be 10. Sine is opposite over hypotenuse. Okay, so we do the trig thing on that, and this would be sine of 20 degrees. All right, that needs to be really automatic for you. So if you don't see that, you need to work on that. Give me a shout if you're having trouble with it. Okay, and then the B component is pointed down, so it would need a minus sign, minus 10. All right, and there's no X component. We can tell that by inspection. All right, and then the C component is pointed up. All right, so that would be a plus 15 sine of 40 degrees. All right, so you should calculate that on your calculator, and in Matlab verify that our Y is 10.89, and that's the Y component. Okay, so if we wrote down R in terms of its vector components, it would be minus 2.09 I plus 10.59 J. Okay, you could also write that in terms of magnitude and angle. Okay, and so if you take 2.09 squared and 10.59 squared, add them together and take the square root, you get 11.09, all right, at an angle theta. All right, so what is theta? Well, you can calculate that. That would be a tan of the Y component divided by, well, I told you, you can use a tan 2D in Matlab. Okay, so you can use a tan 2 on your calculator, give it the Y component first, and then the X component is minus 2.09. All right, the signs matter, right? So that's what gives you the quadrants. And so when you calculate that, you get theta is equal to 100.86 degrees. Okay, so you should be able to do that kind of calculation. This shows you a little bit about resultant forces. We're going to do some practice homework problems on this. Give me a shout if you have any questions.